am ready to start, yeah.
Okay. Hello, everyone. Thank you for joining Data Connect 2021. Welcome to the Data Engineering track. My name is Ruben Barrios, your host, and our co-host today is Joanna Perdomo. We will be moderating the chat and QA for you during this session. Today, we have our guest, John, and he will be talking about using streaming data pipelines in the cloud to achieve success with data-oriented business problems. John is a distinguished engineer at Optum, focusing on how to use data at scale. He has been an architect and technical lead on various efforts, including Optum's Analytic Common Capability, a platform for executing patient analytics in massive parallel environments. And he is currently leading the architecture and platform teams for the OptumCare data platform. Without any further, I will hand this over to the speaker. Thanks for being here, John.
Thanks, Ruben. I'm really excited to be talking today. I've seen a lot of the past DataCon LA videos posted on YouTube, and they've been really helpful. So I'm happy to be contributing one of my own. So today I'm going to be talking about, my slides are paused. All right. So today I'm going to be talking about who the target audience is and if you want to be in this session versus some of the other things that are happening right now. A little bit about me and my background, what we're doing with OptumCare and the perspective that that's going to be bringing to this talk, about our journey to streaming in the cloud, some lessons learned, and some ways that you can apply all of that to what you're doing on your own. So if you're a developer, architect, or analyst interested in pulling many disparate sources of data together, not building individual point solutions, but capabilities that can really transform your enterprise, and trying to bring enterprises into the 2020s, whether they're ready for it or not. I am not going to be getting very technical. I have a few snippets of code. We'll be talking about technical things, but I don't have any deep examples or demos. So I've been at Optum for 13 years now. I'm a distinguished engineer. And as Ruben said, I'm focusing on design, architecture, scaling. And my current project is our care data platform. What is OptumCare? OptumCare is part of Optum, and it is a rapidly growing collection of primary care offices, walk-in clinics, ambulatory surgical centers all over the United States. There are 20-something acquisitions that have been done now, and it's growing very, very rapidly. What you see on that map is about $20 billion in revenue, and the business plans to go to $100 billion by 2028. And in order to do that, there's going to be way more acquisitions happening and way more data that we need to be integrating. For every one of these acquisitions, we have not done any back-end integration. They're all running in whatever data center they were in when they were acquired. And it's a real challenge to figure out how the business can use that data and make business decisions when you have data islands spread all over the place. So it's our job to fix that, and I'm going to talk about how we're doing that. We really want to modernize how the business is using data. If you know much about the healthcare industry, it's significantly still running on batch processing. Some of it's moving to streaming, but the majority of it is batch processing in the background. And that means data is delayed, it's expensive to process, and bringing many systems together is difficult. What we really want is a cloud scale data warehouse, a modern data stack, in order to bring data in and make it available to a lot of different uses across the enterprise. We want to have a single one-stop application, a single one-stop place for all applications to use data, but we're not interested in just building another data lake. There are many regrets for data lakes built over the last 10 years, and we need more capabilities than a traditional data lake would have. And in addition to that, because we're dealing with healthcare data, we want to make sure that we're being responsible with it. We have very strict security requirements. We want to have strong data access controls so that only the people that need to see the data are able to see it. If you've been in the data engineering industry for the last few years, you've probably noticed that there's been a huge amount of transformation in the tools and architectures that are available. We spent a lot of time putting together Hadoop systems, using MapReduce. They're difficult. We don't want to be doing that again. There are higher level tools available, such as cascading or Beam. And those abstract away the underlying engine. They're much more approachable. They're faster to develop, but they don't expose the full power of the underlying engine either, because they're an abstraction on top. Apache Spark has really come into its own the past 5 years or so, and that arrived at the point of big data. We're not talking about big data much anymore. Now it's all about the cloud, streaming, and how do we move the enterprise forward. For teams that did do a lot of work with Apache Spark and data lakes, I'm seeing a common pattern that those teams are often left with very disappointed customers, very expensive, fragile jobs, and lots of technical debt. So how do we build a modern system that doesn't repeat all those mistakes of the past? There's two very common streaming architectures. Lambda got a lot of publicity 5-7 years ago when Nathan Mars introduced this architecture. It was very early hybrid architecture. It enabled low latency streaming for recent data, but it required batches in the background to fully update data sets. And it was really expensive to develop your logic twice, once for batch and once for streaming. A more modern architecture is the Kappa architecture, which has been publicized by Confluent. And it has streaming at the core, which, because from Confluent, means Kafka. That's great. It's a powerful tool. And it brings a lot more capable APIs, such as K-Streams, K-SQL DB, and the ability to write other microservices to build your business logic. And it can get very low latency because your data is streaming in, and you can react to it immediately. But these can often still be expensive to develop. And even if you're bringing all of your data in with a Kappa architecture, Kafka is not a particularly great way for your users to experience your data. You really want to have a modern cloud scale data warehouse to make your data available to the business in a way that they're comfortable consuming it. And if your business is anything like ours, that usually means SQL. Again, we're going to need fine-grained access controls in order to make sure that we're being responsible with the data, auditability, make sure that the data is being used correctly, and scalability, because this is 2021. Everybody's got an enormous amount of data. Everybody's growing. You really need the scale of the cloud in order to do that. Another challenge is we don't often know all of our access patterns when we're designing an architecture up front. You need to make data available to other applications in a variety of ways. And technology is changing so rapidly these days that you don't want to limit yourself in how the data is going to be consumed, because a year from now, there might be some brand new technology that you didn't even consider, and you need to figure out how to make that work with your application. So you don't want to be so restricted that you can't use the new tools. So how do you do that? Coming back to first principles, you really want to make sure that you're doing streaming first. You need to get your data in quickly, easily, reliably. You want to be able to process the data through a bunch of different things, and then have the data available to be consumed by your users when they need to consume it. That sounds simple, but it's not. So a really simplified architecture might look something like this. Your source data is coming in, and that could be from a variety of different technologies: SQL Server, Oracle, Elastic MapReduce. No. EMR is electronic medical record. And there are lots of different standards that are sending data into healthcare environments, and you need very specialized tools to consume those. Once you've identified your data, how do you get that in? You generally don't dump your SQL Server directly into the cloud. You want to bring that in with a tool that can do that intelligently. bring it in, only bring in the modified data, find a way to get it into your Kafka environment so that you can do more stuff with it. And I'm going to be talking more about Kafka Connect and Debezium in a little bit. Once your data is into your streaming platform, then that's great. But what streaming platform should you choose? Kafka is super popular, but there are tons of other options. If you're on Azure, Event Hub's an option. There's Apache Pulsar, and many, many more depending on what your needs are. Once you've got the data into Kafka, then you'll process it with whatever logic you need. There's tons of options there: K-streams, Flink, Beam, etc. And then once it's through your pipeline, then you'll land it in wherever your data warehouse is. Snowflake is becoming really, really popular. If you're on Azure, then there's Azure Synapse and Redshift if you're in AWS, and many more options. For us at OptumCare, these are the ones that we are using, and I'm going to be talking about these ones in a little bit more detail. For data ingestion, if you're on Kafka, then you really want to be using Kafka Connect in order to bring your data in. It's a really, really useful Swiss Army knife with many, many, many different connectors available to choose. Many source connectors, sync connectors, integrate with almost any technology that can produce or consume data. And it works really, really well for static workloads, dynamic workloads. It works in container environments. It's really, really useful, and you can adapt it to lots of different technologies. There are tons of free or open source of connectors available, and some of the other ones require a license from Confluent. And it's possible to deploy it in a lot of different places. You can deploy it next to your data inside the legacy data center. You can deploy it out in the cloud, wherever you need it. Here's a specific example of how you would set up Kafka Connect. So here we're using the JDB source connector, and we have this JSON file that we use to configure it. A few specific things to note in here. We are using Avro messages. There's a huge savings when it comes to the amount of data being transferred when you use Avro, which is a binary format, versus something like JSON. We're also using the Confluent schema registry because that means that you only need to have a reference to the schema in every single message. You don't need to have the entire schema included in every message, and that also cuts down on the amount of data that you need to transfer. The third thing that we're doing to reduce the amount of data going over the wire is to enable producer-side compression. It's an amazing amount of savings to enable compression on the data that's coming in from Kafka Connect. And one lesson that we didn't learn until later than we would have liked is you really need to set the batch max rows to something particularly high. Here is bolded. It's set to 16,000. When this is set to the default, which is whatever your JDBC connection is going to default to, usually like 20 or so, it's excruciatingly slow. So this should be one of the first parameters that you change. Some other pain points that we've seen are that these connector definitions don't deploy well in a typical CI/CD environment. We would prefer to just embed them into a Kubernetes image and deploy that and run it. And these really need to be set up at runtime by calling the REST API in order to define them. So in this example, we're using curl to hit our server and turn on the connector. Another frustration we've had is that the elasticity could be improved on many of the connectors. If you're bringing in a table with 1 billion records in it, Kafka Connect is going to run that on a single process, a single thread, and it's going to take a very, very long time for it to come in. And not Kafka Connect, I'm sorry. The JDB source connector or Debezium. Maybe there's some other connectors that are more optimized, but the ones that we've looked at so far are a little slow for really, really big tables. But you really shouldn't be using them for big tables. You need to bring the data in once, and then you want to stream it in, stream the changes. So the next big component in the architecture is your streaming platform. I've already talked about this a little bit. There's many, many to choose from. I'm not going to spend too much more time on this because this is a very infrastructure specific choice based on whatever else you have in your app, in your stack. And there's a lot of cloud native options. There's MSK if you're on AWS, Azure Event Hubs that I've already mentioned, Confluent if you want to use their stack. And then there's a bunch of open source versions as well. You're processing the data. There are many, many options to choose from, and it can be overwhelming. It could be a full-time job just to keep track of the different technologies that are available and what you want to be using. Historically, a data lake would be bringing data in, dumping it in the data lake, and then all the teams come in and they do what they need to process the raw data, have a ton of different jobs, interdependencies, and long cycle times. We really want to be moving towards a modern streaming approach, streaming first, transform it, ingest it as it arrives before you fully land it to your warehouse. You need strong metrics, and you need to make sure that you're keeping these things in mind as you're choosing what tools do you want to be using for your streaming pipeline. In order to choose your tools, you need to figure out what do you want to be executing in your pipeline. This is a simplified example of our pipeline. We have raw topics landing in Kafka. We're running it through some data lineage standardization. We're running data quality, dealing with how to reconstitute the CDC, and doing some more stuff. So I'm going to walk you through a few of these on a little bit more detail to get an understanding of what we're doing, why, and some things that I haven't really seen in a lot of other platforms that might be useful to you. So data coming in from Kafka Connect has a different structure to the message depending on what tool is bringing it in. So I have a few examples in the slide here. I hope you can read it from your screens at home. This first example on the left is a Debezium message coming in as a change data stream on a database. So there's a transaction. If it was an update to a record, then we would have the before information. We have the after information, and you can, if you expanded it, you could see the full payload of what the data was in that record that was modified or added to the database. And then we have a bunch of metadata available about the source of the data. What database did it come from? What table? It gets down to the actual commit LSN of the database so that you can really tell exactly where the data came from and when it changed. The example on the right is coming in from the SQL source connector. And this is extremely flat. It doesn't have any of the other metadata associated with the database. It's just a listing of the tables and their values. Why is this a big deal? Well, if you're bringing in the data through Kafka Connect, landing it in Kafka or whatever your streaming platform is, it would be bad engineering to tightly couple the rest of your pipeline to the specific tool that sent the message in. It really restricts you from making changes. And if you're bringing in data from as many databases as we are, then they're bound to change over time. We recently just had a Sybase database that was upgraded to SQL Server, and we're now getting messages that are a very different schema. And if we weren't standardizing this, then we would have to go change every bit of logic through the rest of our pipeline that was working with that data, because suddenly it's showing up in a different place in the schema for the data that's coming in. We've looked at quite a number of different Kafka connectors as we're pulling in data from different sources, and every single one of them has a different schema. So what's the solution? We've written a Kafka Streams app that is subscribing to almost all of our incoming topics. It's a very lightweight app. It runs very, very quickly, and it can easily keep up with the data as it's arriving. It looks at the structure of the incoming message on every single topic, and it reformats the metadata into a consistent envelope for the data so that we can always expect the payload to be in one part of the schema, and we can always expect the metadata to be somewhere else. And then the rest of our streaming pipeline can easily process the data without having to be tightly coupled to how the data came into your system. I've pulled one short example out of our code here, and this is looking at data that's come in from the JDB source connector. All it's doing is creating a new record to go into a new Kafka stream, and we are basically embedding, hey, it came in from the JDB source connector. If it was coming from a file, then we would have an offset in there. If it came from Debezium, then we wouldn't have to embed a create event. We could pass through the type of event, whether it was insert, update, or delete, and then a timestamp. And it's really easy to extend this to any other metadata that you want to include for your data lineage, such as the source organization that sent it, topic names, anything else that your platform would need in order to keep track of your lineage. Data quality is becoming very, very important for data science, machine learning. Your analytics are only as good as your data. And data is often really, really dirty. You want to make sure that you understand the quality of your data as it's coming in for a variety of reasons. For us, we want to be proactive about the data. Be proactive if something breaks. We can set up alerts to make sure that whatever we're expecting to come in is coming in. If, for example, somebody changed a system over the weekend and now everybody's birth date is coming in as January 1st, 1970, then that would be a problem. And we have the ability to set up alerts on that. One thing that most of the data quality frameworks that we've looked at in the open source community do is they reject bad data. And for us, dealing with healthcare data, that's a bad thing. We have important data like a diagnosis, a procedure. Those might be an anchor record for something really important like cancer or heart attack. And we really can't reject the data just because one of the fields was a little weird. We need to make sure that we're measuring it and trying to keep the data going through the system as best as possible so that you can get downstream. And even if it's not as useful as a full record, we can still do some stuff with it. How do we do that? So we've put together another Kafka Streams app, and it can be configured to watch the quality of the data that's coming in. As an example, we have defined a rule, email address rule. So is it null? Is it not null? Is it conforming to the proper format of an email address? And when a record comes in that doesn't conform, then we're going to stamp it with this metadata, add it to our message envelope, and send it downstream so that we are permanently marking this record as not passing a particular quality rule on a field. The other thing that we're doing with the output of this is we're sending the metrics of the data quality directly to our monitoring stack. And this gives us the ability to report on it, to watch it over time, to set up alerts. And I pulled out a short section from our Grafana dashboard when we were running a load a few days ago. And you can see something happened with the data that was coming in between 10:10 and 10:11. And there were probably some really bad records that came in, and then it it got resolved. If it didn't get resolved, then we would need to go figure out what's going on and how to fix that. So coming back to our example data pipeline, we've looked at the data lineage standardization, the data quality, and now I'm going to talk about some of the more heavyweight things that you might need to do in your pipeline. So I have this axis on the bottom. On the left side are low latency, low complexity, things that need minimal state. You can execute them really, really quickly. But as you get further and further into your data pipeline, you probably need to do things on your data that are much heavier weight, higher complexity. You might need more state in order to figure out what you're doing with it. You might need to send messages out to other services to get a response back so that you know what to do with that record. And you generally want to put those things later in your pipeline. Be able to do the things that are lightweight early, get those done, and then wait as long as possible to do the heavier weight things. I'm not going to go through every single box, but we'll pick a couple of these and go through it. So I've mentioned CDC or change data capture a few times. This is becoming a really, really critical capability in order to bring data from disparate systems into the cloud, into a modern data stack, and be able to understand what's going on with the data. So change data capture is usually going to look at the logs on your database and monitor them. And when it sees some data change, it will read the log and turn that into messages that it sends to your consumer to be able to understand what changed in your data. The problem is that most streaming ingestion frameworks are really only designed for append only. So by default, a Kafka topic is append only. You can just take in new messages, and if you configure the topic for compaction, then you can overwrite older records, but that's not always useful. If you look at other frameworks that are designed to get your data into something like Snowflake or the Databricks Delta tables, they're almost all append only. And that does not work very well with a change data capture approach. So you need to have some additional steps in your pipeline to be able to figure out, what do you do with this message? Is it an insert? Is it an update? Is it a delete? And get those applied to your data so that when it lands in your data warehouse, it's not just a bunch of history. You want your users to not have to think about applying the deletes before they consume the data. They just want to get the copy of the data as it exists. So how do you do that? There's a lot of choices. I've already talked about some of them, and there's a lot of ways that you could do it, but I'm going to talk about a couple of them here. So if you're familiar with Snowflake, they have several ways to execute code within Snowflake itself. You can define a change data stream on an incoming table and then execute tasks as the data has arrived. And so you can define a stored procedure that you want to execute on the incoming data, and then it can go figure out how to merge that incoming record, whether it's a delete or insert, into your final table so that it's ready for your consumers to use. One of the downsides that we've seen doing it this way is that it requires quite a bit of code for every one of the tables. You need to enumerate every single field in your table into your merge statement, and it has no support for schema evolution. It can be very fragile. So if your upstream databases change, if the DBAs over there decide they want to add some columns and your streaming system from Kalka Connect picks that up, it's going to break really hard when you try to insert it into Snowflake here. An alternative to that is to use the Databricks capabilities in Delta Lake. So we have our data coming in from Kafka, streaming it in after we've stamped the lineage and data quality information on it. And we're landing it into a raw table in Databricks. From there, we have the ability to understand it, work with it in whatever code we need, whether it's the Spark code we're writing in Scala, you can write Python, and really do a lot more higher level work with APIs than a stored procedure that you're writing on Snowflake. One of the things that's been extremely useful to us is the ability to get the schema registry metadata available in the code as you're using it, so that whatever the schema of the message is, it comes in and you can access that immediately within Databricks without having to go rewrite your stored procedure every time your schema changes. Another thing that's been a big challenge for us is flattening the data. If you go back to our examples, we have data coming in inside an envelope where it's a complex schema. So we have data coming in, and here we have basically 3 items at the top level of our message. We have quality in some topics, we have our payload here, we have metadata. And if we just land that directly to a table, that means that we get 3 columns that are basically unstructured data. And those are usable within a cloud warehouse, but users don't like that. It's also not particularly performant. So what we've done is flatten the data, and basically every one of the columns in our payload becomes a top level column in the outgoing table. And if we were doing that in Snowflake streams and tasks, we would need to write hundreds and hundreds of lines into thousands of stored procedures. And we found that Databricks is able to do that with a single line. You can just write select star from select data.star from whatever your table name is, and it will automatically flatten your data to allow you to work with it without having to enumerate every single column. The last major thing in this simplified architecture is your warehouse. So what are you doing with it? Where's it going? Who's consuming it? An enterprise like ours has been using SQL since way before I was born. And SQL is just a fact of life. You need to support SQL for almost all reporting tools and queries. It's got an entire ecosystem that users really like. And it's difficult to bring these tools directly to a streaming platform like Kafka because it's just a different paradigm. And so what a cloud scale data warehouse does is it allows you to present that data to your users in multiple different paradigms, access it through SQL, put some REST APIs on top of it. You can also populate other applications, populate a Fire repository, and let your users access the data from whatever tools they need to. So what we've talked about today is high-level architecture, Kappa versus, I didn't have a slide on it, but delta. So the ability to not just do all of your transformations in stream, but to really think about how is the delta changing, how is the data changing as it comes into your environment. We've talked about some major components for your streaming pipeline, your data ingestion, how you're transforming your data, how you're persisting it, where you're persisting it. And we've gone over some lessons learned, tricks for reducing coupling between your things. And we talked a little bit about our streaming data quality. So Ruben, do we have any questions from the chat?
Yes, we have a couple of questions. The first one is when you mentioned about the Kafka Connect example.
Okay.
That elastically could be improved for many of the connectors you have looked at. There are any workarounds or other options that you recommend?
So from what we've looked at, the fundamental unit is a table, and you can break out your connectors so that you have one connector per table. But beyond that, if you need higher performance, then you're better off bringing your data in through some other path, like a single batch dump, and then subscribing to changes from there. It could be many, many hours to bring in billions of records. And if that's a one-time upfront thing you're willing to pay, then great. But Kafka Connect is not going to allow you to break a single table into multiple threads right now.
Okay. The other one is, at what scale would you recommend a company transition to streaming? How do I convince my tech leads that introducing a streaming pipeline will save us time if we don't already have one?
So every enterprise is going to be different depending on what level of risk and what skill sets the team has. And so it's really more about how a streaming stack can enable your business. How can you make the justification to make a change like that? And for us, it's been about data latency. So we have had batches coming in. They used to be monthly batches. Most of them have been migrated to weekly batches, and some of them are nightly batches. But those get ingested and they don't get published until the next month when we have a new copy of the data. And one of the things we learned over the last 18 months is it would have been really nice to have a streaming pipeline to be able to look at real-time data coming in as COVID patients are hitting a lot of our clinics. And so that's really helped us to justify to the business that, hey, you need to move to streaming because there are definite advantages. You need to make sure that you're not investing in it just because you can, but that there are strong reasons to be able to go there. It's usually about the latencies, but also about scale. And it's going to be different for every business. I don't have anything more specific.
Okay, thank you, John. So we're almost run out of time. So I want to thank you, John, for your presentation, and thank you all the attendees for the questions and interaction during these sessions. You can contact the speaker directly if there is any further questions regarding to this topic. And please remember to provide your feedback using the form that will be provided in the chat box. Thank you again, everyone, for joining today's presentation, and I hope you gained some insights from this session. Have a wonderful day, and thank you for being part of this year's DataCon LA. Thank you, John, for your presentation.
Thanks, Ruben. Bye, everybody.
Bye-bye.